Hello, my name is Andrew, and this is my circuits lab for Physics 2212. For this lab, I'll look at different circuits and predict the behavior of circuits in series and parallel, particularly looking at a computer model of these circuits and comparing the potential difference in current of the experimental and computational models. The main result is that the expected and experimental values for current, which we found in part 1, and voltage, which we found in part 2, are equal. So here's some of the concepts and formulas that I used in this experiment. One was the loop rule, which is that in a closed circuit, the change in voltage is 0. Ohm's law, voltage equals current times resistance. The node rule, that the current in to a node is equal to the current out. The linearization formula, which is used to find the RC. And then resistance in series is the sum of all the resistors, while in parallel, it's 1 over the sum of all the resistors. The initial conditions for the part 1 of the experiment is that there's two 1.5 voltage batteries, two resistors, one of 47 ohms and one of 100 ohms. The circuit is a system, which is an in-series circuit, and the surrounding is everything outside the circuit. We make the assumption that the wires and ammeter have negligible resistance. For the circuit on the left side, we find the total voltage by adding up the two batteries, which are both 1.5, to find the total of 3 volt. Since the circuit is in series, we add up the resistors to find 147 ohms of resistance. And then we use Ohm's law to find the current, which we find to be 0.0204. And we know the actual resistance is 0.02 amperes because of the nodes rule. These two values are very similar though, so basically no difference. And then the circuit on the right side has a voltage of 3, but 0 current since it's an open circuit, not closed. By labeling the points A through H in the circuit as such, we can use the voltmeter to look at the voltage between 2 points. And if we do so, we find the following table. And when we add up all these voltages, we find that the sum of the segments equals 0. This is in line with the loop rule, which I mentioned earlier, where in a closed circuit, the change in voltage is 0. The current, however, remains the same at 0.02 amperes because the voltmeter's resistance is infinitely high in this virtual circuit. So here's a graph of the voltage. So we can see that it starts at 3 volts at B, stays there for C, drops when it goes across the resistor, and then stays the same from D to E because it's just wire, and then drops by even more because it's more resistance across the second resistor. And then the rest is just wire. When the ammeter is connected in parallel to the 100 ohm resistor, the current is 0.06. This makes sense because less current travels through the 100 ohm resistor. And then the following is the resistance at each of the resistors, using voltage and current to confirm it. Part 2 of this experiment is set up differently than part 1. There's only one battery and it's 9 volts. There's a 10 ohm light bulb and there's a 200 millifarad capacitor. When this circuit is all connected up, the light bulb lights up but then dims out until it's out of light. This is the process of the capacitor charging up. When the battery is disconnected, the bulb and then the circuit is reconnected up without the battery lights up and eventually dims down again. This is a capacitor discharging. The time to charge and discharge the capacitor with the 10 ohm light bulb is 6.34 seconds and 11.56 seconds for a 20 ohm light bulb. The time to charge and discharge was the same in each case. Using a 30 ohm light bulb, a voltmeter, and a stopwatch, I recorded the voltage at several points in time as the light bulb dimmed after connecting the battery into the circuit. I used the equation log delta V over delta V initial equals negative time over RC in order to linearize the RC values. And when I put this table into Excel, I found a slope of negative 0.1669. And we know that the slope is equal to negative 1 over RC. So that made the experimental value for RC 5.992 seconds. I meant the experimental RC value. And the RC value that we expected was the resistance times the capacitance, which was 30 ohms times 0.2 farads, which is equal to 6 seconds. The experimental and expected values were very close for this, similar to the current. There weren't many sources of error for this lab since it's all virtual, but some source of error may have happened when recording the voltage using the stopwatch and trying to time that out. But this error was very minimal because 5.992 is very close to the expected value of 6 seconds. And then some discussion questions were, if I was doing this lab in real life and use an actual ammeter instead of the ideal simulated ammeter, I would find that the ammeter would have a small resistance rather than zero resistance, which would have resulted in a reduced current value, because higher current means low, or higher resistance equals lower current. If I was doing this lab in real life and used a real battery to charge a real capacitor with no resistance in the current, I would find that, well, the ideal model would charge the capacitor instantaneously due to the assumed zero resistance in the wires. A real capacitor would charge quickly but not instantaneously because there is some resistance in real wires. Thank you for watching.